Our first speaker today will be Susan Richardson. She's from University of South Carolina, and she'll be talking about the transforming power of chemistry, uncovering emerging water contaminants, and making drinking water safe. So Susan, the floor is yours.
Here we go. Can you see that okay?
Yep, you're ready to go.
Perfect. All right. Well, it is such a huge honor to be invited to this special session. And I'm going to be talking about our latest work in drinking water and trying to make it safer from emerging water contaminants. So when you think about that glass of drinking water, you might be like me, you have one right here with you and wondering what could be in that water. A lot of people are concerned about pesticides, but I can tell you it's a rare day that we see pesticides in finished treated drinking water. Bisphenol A is a concern, and a lot of people have switched to those stainless steel thermoses to avoid that. It's added to some plastics. Pharmaceuticals, people have been concerned about having other people's drugs in their drinking water for quite a while, but I can tell you it's a rare day that we see pharmaceuticals in finished treated drinking water. And when we do, they're low nanogram per liter level. So it would take billions of gallons of drinking water to get the equivalent to a pill of somebody else's drugs. 1,4-dioxane is a concern, and the EPA has found this industrial solvent in about 12% of our drinking water supplies around the country. So that is one to keep your eye on. PFOA, perfluorooctanoic acid, is one of those PFAS compounds. They call them PFASs now. And this is definitely a concern for the environment, but it is a rare day that we see it at appreciable levels in finished drinking water. When we do, it's usually very low nanograms per liter. And finally, you might think about lead. Any of you who live in Flint, Michigan, or used to the last few years, you had a high incidence of lead in your drinking water, big concern. And even in Washington, D.C. in the early 2000s, there was a release of lead from the service lines, from the pipes. So that is something to keep your eye on always. And these chemicals may or may not be in your drinking water, but there's always something that's in your water, always. And that's DBPs, disinfection byproducts. And these DBPs are formed when we treat drinking water with these different disinfectants: chlorine, monochloramine, ozone, chlorine dioxide. Very important to kill the harmful pathogens in the water to make the water microbially safe to drink. But what happens is those disinfectants will react with natural organic matter that's just naturally occurring in our lakes and our rivers, very safe stuff. And then we also have saltwater intrusion into our water supplies, especially if you live along the coast. You can have high levels of bromide and iodide coming in your source water, and that will contribute to the formation of more toxic brominated and iodinated disinfection byproducts. So I want to point out that DBPs are not like traditional environmental contaminants where they are released from industries or released from wastewater treatment plants. These are things that are only forming during drinking water treatment, so they can be a real challenge to identify. And these disinfection byproducts are always in your drinking water, and they're usually at part per billion levels. So they are there at 1,000 times higher levels than all those things we talked about on the previous slide. And here's why this is important. DBPs have been linked to adverse human health effects, including bladder cancer, miscarriage, and birth effects. And I can count on two hands how many environmental contaminants have been definitively linked to an adverse human health effect. DBPs are one of about 10 of those environmental contaminants. And that's because we have many human epidemiologic studies done both in the US and many cities in the US, and also many cities around the world that show an increased risk of human health effects from DBP. So this is something real in the population. And we have, though, much of that is unknown. This is from a nationwide occurrence study that we conducted back in 2006. And we found out that we still have about 70% unknown halogenated material formed, DBPs, in chlorinated drinking water. In this study, we were going beyond the regulated trihalomethanes and haloacetic acids and quantifying for the first time many of these more toxic, unregulated DBP classes. But we found that these were only tiny slivers of the pie, and they were still missing a lot of material. So hence, this is my quest. My big quest is to find out, what is this unknown material? What's in our drinking water that we don't know yet? Which ones of these things are toxic that we need to focus on? And then finally, how can we make drinking water safer? How can we remove these things or keep them from being formed? I think we have good water, but I think we can do better. We only regulate 11 DBPs in the US. We have these 4 trihalomethanes, 5 haloacetic acids, bromate, and chlorite, but we have now identified more than 700 DBPs. And there's less known about the occurrence and toxicity of these unregulated DBPs. What's really important to note is that none of these regulated DBPs cause bladder cancer in the test animals, in rats and mice that we do the toxicology studies in. But bladder cancer is what we see in the human populations. So a lot of scientists like myself believe that it's something other than what we're regulating and controlling that's actually responsible for the human health effects. So this is why this is still an ongoing issue. And iodinated DBPs are highly cytotoxic and genotoxic. This is work by Michael Pleva at the University of Illinois, where he's looking at the cytotoxicity. This is like cell death in mammalian cells, and also genotoxicity, which is DNA damage that can lead to cancer. And as we go across the chlorinated to brominated to iodinated DBPs, we vastly increase the toxicity. So for example, iodoacetic acid is more toxic than bromoacetic acid, which is way more toxic than chloroacetic acid. And nitrogenous DBPs are also highly cytotoxic and genotoxic. So things like haloacetonitriles, halonitromethanes, haloacetamides. So similarly, as we go across from the regulated trihalomethanes that are not genotoxic and are barely cytotoxic, across the regulated haloacetic acids to these nitrogenous DBPs, we vastly increase the toxicity. And it's important to note that no iodo DBPs or nitrogenous DBPs are currently regulated. So I talked about traditional issues before, with natural organic matter being the main precursor for the formation of DBPs and the introduction of saltwater intrusion into our water supplies. But we also have other new impacts on our water supplies, including hydraulic fracturing, wastewater, where it's going on in a lot of places in the US. We have coal-fired power plants all over the place that are also switching to newer technologies where they're releasing high levels of bromide and iodide into the environment, just like the hydraulic fracturing plants are. And here we are. This is my student, Hannah Libator, one of my first PhD students since I moved to the University of South Carolina. We're on a lake in North Carolina, and this is a coal-fired power plant here. It's releasing very high levels of bromide and iodide in the outfall behind it and going into a river that leads to downstream cities' drinking waters. We have climate change going on, increasing drought. And I like to show this picture because when we think about drought, we tend to think about the western states in the US, California, Arizona, Nevada, but this is the state of a drought in the southeast that went on for about 6 years, where we got about half the amount of rain than normal. This is Lake Lanier, and this is just showing a small portion of Lake Lanier that serves a major part of the city of Atlanta, Georgia. It has about 6 million people in that city now. And you can see these are boat docks on dry land here. They're on dry land. This was a very desperate situation they had back in 2009. We have growing populations, increasing water scarcity. So we're looking at new water resources, including wastewater reuse. And I'm not talking about de facto wastewater reuse from treated wastewater going into our rivers and downstream to new cities' drinking water supplies. I'm talking about directly reusing wastewater, turning it into drinking water. There's a big push in the US now to go more in this direction. We also have some new desalination plants being built. The latest one was in the San Diego area in California for the US, but there are many around the world. So part one to my results, I'm going to show you two parts. And this first is the impact of hydraulic fracturing on our drinking water. This was Hannah Libator's main PhD work. And the idea is what happens now when these fracking waters are released to our drinking water supplies. So we are pretending we're like a drinking water treatment plant, and we are chlorinating. This is aqueous chlorine. This is chloramine that we're treating with in the lab to pretend we're like a drinking water treatment plant. And we're taking these fracking wastewaters and treating them. So here we have the raw feed. This is after a lot of the petroleum, the oil and gas has been removed from the fracking water. So it's still got a lot of petroleum in it. And the fracking wastewater we have for this study is from the Barnett Shale in Texas, and they are very water scarce. So they're actually trying to clean up the fracking wastewaters to be able to reuse them again to frack another well. This is really important because it takes millions of gallons of precious water to frack a single well. So I think it's good to try to clean it up and reuse it if possible. So they're treating with these different membranes, 2 micron, 0.1 micron membrane, and then finally the nanofiltration membranes. And you might think, well, wow, this is great clean water. We're all good. This could be released to the environment. But what happens is this water has exactly the same amount of bromide and iodide as this original fracking raw feed water. Really high levels, much higher levels than anything we would ever encounter in the US. And our concern is the formation of these more toxic brominated and iodinated DBPs. So we're using liquid chromatography, high resolution mass spectrometry, LC mass spec, to try to identify these DBPs. We are using an Agilent quadrupole time of flight mass spectrometer for this work with negative ion electrospray. And we found 2 new sulfur containing brominated DBPs with this particular mass spectrometer. We see 4 isomers here with this particular molecular weight here, molecular mass. And by the way, with high resolution mass spectrometry, we're getting decimal places on these masses. So these decimal places, this exact mass, will point to a unique assignment of atoms in your formula. So we can know from this accurate mass what the molecular formula is. And here's our theoretical mass here. We can see a nice match of this to our unknowns. And we can also see nice isotopic patterns, because if you have bromine in your molecule, this is a beautiful pattern for one bromine containing molecule where these are separated by 2 mass units. And if we look at the theoretical pattern for this particular formula, we see a beautiful match of this pattern. By the way, here I forgot to mention, we had 1 isomer for this compound that had 1 bromine and 2 sulfurs in the molecule. So now we want to do MS-MS because we want to break this molecule into pieces. When you do electrospray mass spectrometry with LC mass spec, it's a soft ionization technique, so you only get the molecular ion. You're not breaking it to pieces yet. So we do something called MS-MS to break it into pieces. So we see this loss of HBr from the molecule. We see C12H24O being lost, which is a shame because this is what we want to try to figure out what the structure is. And then we see this fragment of bromine here. So unfortunately, this didn't tell us much more than what we already knew from just the starting MS, the formula of this thing. But we figured it's likely a surfactant-based DBP because we have an SO4 part of this molecule. But from what class of surfactants? Could be a sulfate. Sulfate would be an SO4 group, or another sulfur-containing surfactant. So we really needed MS to the third, MS, 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 to get more structural information. We want to know what the identity of these structures are. So we actually drove down to the Florida Magnet Lab in Tallahassee, Florida, got time on their FTMS instrument with their 21 Tesla magnet, and we're doing ultra high resolution mass spectrometry now because that instrument gets more than 1 million resolution. And because of that, you get 5 decimal places on your masses here. And it turns out that these data indicated that these were not sulfate-based DBPs, but brominated sulfonate DBPs. And this is how we knew this. First of all, we see a fragment, the loss of CO. So that means that one of the oxygens is bound to a carbon and it can't be all in an SO4 group. Here's another smoking gun here, loss of CH2, SO3. So you see clearly you've got a sulfonate group and not a sulfate group. Then when we look in our undisinfected fracking wastewaters, we see two prominent ions in that mass spec data where things that could be precursors, one that has one sulfur, one that has two sulfurs. And it turns out that a common type of surfactant that's widely used in oil and gas extraction activities in the fracking industry are these olefin sulfonates. We didn't know this to begin with until we got these data. So here's what an olefin sulfonate looks like. Here's a sulfonate group. And the olefin is key here, this double bond, because if you have aqueous chlorine, you have HOCl, and that means you can pop a chlorine and an OH group across this double bond. And if you have high bromide, like we do in these fracking wastewaters, that'll turn it into HOBr. We can pop a bromine and an OH group across the double bond, and that could explain exactly what we're seeing. So we are seeing this one on our real fracking wastewater. We also see a dimer of that as well. And it turns out from the production of these olefin sulfonates, side products are also present in these commercially available surfactants. So it's not like the fracking companies are buying 99.9% pure of an olefin sulfonate. They're buying technical grade surfactants because you're using these in ton quantities in the fracking industry. So these have a lot of impurities in them, including disulfonates, as it turns out. And we see this disulfonate in our fracking wastewater. Note the double bond here again. This is in our real fracking wastewater and could explain our disulfur containing DBP. We also see a doubly charged ion for this as well by mass spectrometry. So what my student Hannah Libator did was she called up, got on the internet first, found a company, a random company that sells these olefin sulfonates, called them up and asked them if we could get a free standard. We only need a little bit as analytical chemists, we only need a tiny bit of standard. They sent us a free standard. And my student Hannah was in tears the day that she got these data. The black trace here is the gas extraction wastewater, our fracking wastewater, real fracking wastewater. The red is that olefin sulfonate technical grade standard that she randomly called out the company for. And you can see it's this beautiful match. It's as if that fracking company in Texas is using this exact same technical grade surfactant that we got our hands on. Then when she chlorinated that in the lab, again, we see a beautiful overlay of many of these peaks. The black is our real fracking wastewater that's chlorinated. The red is that technical grade surfactant that's chlorinated. So a beautiful match of many of these peaks that we're seeing. And of course, with the real fracking wastewater, we're also going to get some other DBPs because it has other precursors in that fracking wastewater. And we saw some things we think are bromosultone sulfonates. I've never heard of sultone sulfonates, but this is the only thing that made sense for the mass spec data. We also see these bromohydrin sulfonates. I mentioned popping a bromine and OH across a double bond with an HOBr. And then when we started looking at those little itty bitty peaks here, we normalized all these small peaks that we had seen before. And we see that in addition to bromohydrin sulfonates, we see chlorhydrins, iodohydrins, and these bromochlorosulfonates. There are multiple isomers for most of these. It was extremely complex mixture. And in the end, instead of just 5 unknown DBPs, we tentatively identified more than 300 sulfur-containing DBPs. And we just published this last year in Environmental Science and Technology. So part 2, I want to show you the next phase, very important study that we just completed, our forcing factors study. And the question we're trying to answer here is, what are the main drivers of toxicity in drinking water? Nobody's addressed this before. This is my student Josh Allen's PhD work. He just graduated a year ago. Here he is at Atlanta Braves baseball game, caught a foul ball. I love this picture. And we quantified more than 70 DBPs using gas chromatography mass spectrometry, GC mass spec. And these were from some very sensitive methods that we created in our group. We can go down to low nanogram per liter detection limits for most of these. We just published this method in Analytical Chemistry last year. And we measured these toxic iodo DBPs I showed you before, these very toxic nitrogenous DBPs here, some other ones as well, and also had Michael Pleva at the University of Illinois importantly measure the mammalian cell cytotoxicity and genotoxicity. And I want to give a shout out to this Restec RTX 200 GC column. This was key for optimizing separations. I normally would use a different kind of column for many years when I was at EPA, never think to change the GC column, but I want to show you why that can be important. Here was a traditional column we were using for many years, a DB5 column, and here are halo acid amides. These are one of the very toxic nitrogenous DBPs, and you see how terrible the chromatography looks here. These peaks are very taily, but if I change the column to this RTX 200, the peaks sharpen up a lot. So for example, dibromoacid amide, you see how that peak sharpens up. And here, this iodoacid amide that you would barely know is there becomes this beautiful sharp peak with the 200 column. So this is how we were able to get low detection limits. This is one of our things that we optimized with GC column. So now I want to show you some results. First, here are the regions of the US that we sampled for this forcing factor study, where they used different disinfectants, chlorine, monochloramine, ozone, different source water impacts, including ones that had high bromide and iodide from saltwater intrusion. I mentioned before, these are plants along the coast here. Plant 2 used chlorine with granular activated carbon treatment. Plant 3 used ozone with chloramine and biofiltration. Plant 4 uses chloramine with conventional treatment. And in plants 2 to 4, the bromide ranged from 120 to 334 micrograms per liter, and iodide was detected at least once in each plant at these levels. Plants 5 and 6 here were heavily wastewater impacted sources, so we had more DBP precursors because of that wastewater being present. These were also very high in bromide, and each used monochloramine for disinfection along with different advanced treatment strategies. And finally, plant 1 used granular activated carbon with chlorine and had very minimal wastewater or other halide impacts. So this was kind of like our pristine plant example comparison. And we had 2 to 3 samplings across the different seasons of the year, because you have seasonal effects with temperature and different things with DBPs. So this was a very huge undertaking. Now I want to show you some results. So I'm showing these in micromolar. These are our unregulated DBP concentrations, all these different classes that we're measuring, those 70 DBPs that we're quantifying. And these are stacked charts here. We have our chlorine plants, we have our chloramine plants. And we also are overlaying this with our cytotoxicity. This is a cytotoxicity overlaid on top of our concentration data. And I'm going to walk you through these data. The first of all, we have plants 1 and 2 that use GAC and chlorine. And plant 1 here had less DBP formation, likely from the use of granular activated carbon. This is a lot like what's in your Brita filter, except here, some plants in the US are using this to remove the natural organic matter precursors. And the idea, if you remove those, then you can vastly reduce the levels of DBPs. And that's exactly what we're seeing here. And we also have reduced cytotoxicity as well that goes along with these lower DBP concentrations. We see lower DBP formation than at plant 2 here. This is lower plant 1 than plant 2, likely because plant 2 has, or plant 1 has less halide impacts here. Now, if we go to the high halide, low wastewater impacted plants, plants 2 to 4 here, we see the plant 4 has higher iodo DBPs in the red and the yellow here. You see that? These are the ones that are very toxic. Also, which use monochloramine for disinfection. And this is also where cytotoxicity is highest. You see cytotoxicity spikes up here with these plants, corresponding to these higher iodo DBPs that are very toxic. And we also identified chloroiodoacid amide and iodoacetonitrile for the very first time in US drinking water in this particular plant. So now if we go to our wastewater impacted plants, plants 5 and 6, we see the highest unregulated DBP formation on 3 occasions, these 3 occasions here, highest formation. But the higher concentration of DBPs did not always result in higher cytotoxicity, but the cytotoxicity did trend well with those nitrogenous DBPs. So you see the cytotoxicity is lower here compared to this plant here from before, doesn't correspond to these high concentration bars. But if you look at the nitrogenous DBPs, these haloacid amides, haloacetonitriles, halonitromethanes here, these three colors here at the bottom. As this goes down, the cytotoxicity goes down, these concentrations go down. As these go up, cytotoxicity goes up, goes down, cytotoxicity goes back down, and so on. So it trends well. And in fact, those nitrogenous DBPs are important drivers of drinking water cytotoxicity. If we plot all of the summed nitrogenous DBPs across all of our plants that we sampled versus cytotoxicity here, we see a good correlation that's significant to the 95% confidence level. All right, so this means that those halocetonitriles, haloacetamides, and halonitromethanes are important drivers. And if we drill down further to just the halocetonitriles by themselves, we find that they also correlate very well with cytotoxicity. And if we drill down further, we see that the dihaloacetonitriles are important drivers of drinking water cytotoxicity. We've got dichloro, bromochloro, and dibromocetonitril. So again, a very good correlation at high significance, 95% confidence level. And these had the greatest influence on halocetonitril cytotoxicity correlations. They're ubiquitous in disinfected water. We see these all the time. Almost any drinking water I've ever sampled, they're there. And these can be present up to 41 parts per billion individually, very high levels they can be. Dibromocetonitril is the fifth most cytotoxic DBP that's been investigated to date. And importantly, there's clear evidence for carcinogenicity. The National Toxicology Program published their results not long ago showing cancer in 2 different animal species. So I think these should be regulated personally. And it turns out the regulated trihalomethanes do not correlate with cytotoxicity in drinking water. If we look first at all the carbonaceous DBPs that include those trihalomethanes and all the other things that don't have nitrogen in them, we see no significant correlation. And look at specifically just the regulated trihalomethanes, also no significant correlation here. So it's likely that they contribute little to the cytotoxicity, the regulated DHMs. So summary and strategies for removal. Drinking water is a complex mixture of hundreds of compounds, and it's difficult to attribute the toxicity solely to any single chemical or chemical class. The nitrogenous DBPs are important drivers of cytotoxicity, particularly the dihalocetonitriles. And dihalocetonitril standards are inexpensive and can be easily measured with existing EPA methods. So future regulation and monitoring would be feasible. Also, the iodo DBPs are important drivers of cytotoxicity in iodide impacted waters using chloramine for disinfection. And there are many of those like this in the country. This is not just this one plant with this situation, but granular activated carbon with chlorine or the use of ozone could help mitigate iodo DBP formation. So we have solutions to these problems. And finally, halide removal strategies, such as ion exchange resins to remove the bromide and the iodide from the water, could help reduce bromo DBP and iodo DBP formation. But of course, this will be more expensive to do, but I think it could be worth doing. Our goal is clean and safe drinking water. I think we've got good water, but I do think we can do better. I want to close by thanking you for your attention, showing a picture of my group here with our mascot from the University of South Carolina. Here we are in our masks, all safe. I want to acknowledge my sources of funding and give a special thanks to Michael Pleva and Elizabeth Wagner, toxicologists I've worked with for many years. We are celebrating now 20 years of our labs working together. Thank you again, and I'm happy to take any questions you might have.
Okay, thank you, Susan. We have time for a few quick questions. And one is fluoride. What's your take on fluoridation? Do you think it's necessary? Oh, wow. That's a very different kind of question. The dentists, the dental folks, researchers too, will say it is necessary, does strengthen the enamel in our teeth and helps prevent cavities. But there is a fine line, and I know that they
lowered the allowable level of fluoride that's added to the water just recent years ago, because there can be some effects if you get too high levels of fluoride in your water. We see that more with people that have well water that's impacted by natural levels of fluoride. You can have mottled teeth, you can have some bone damage. So there is a very narrow, relatively narrow window where it's very effective for teeth, for protecting against cavities, but above that level can cause some other issues. So I think it's fine. I just think the drinking water treatment plants control that very carefully, how much they add into the water at the end of treatment. So I think it's good. You just got to be careful, especially if you're on a well that has high levels of fluoride in there, natural fluoride.
And then one more short question, because we have to move on. It's about continuous monitoring with sensors. Do you use that in your work, and would that be useful, and what's the need for that?
That's a great question. I don't use that in my own work, but some drinking water plants, in fact, many drinking water plants do, to monitor things like the amount of free chlorine or the other disinfectant in the water, to know that you've still got a disinfectant deep in the distribution system. So, it might be disinfected when it leaves the plant, but it's also important to know if it's still disinfected when it comes a mile down through the pipes to your home. So they have sensors in place, ways to measure that in situ. And there's a new inline instrument that can be used to measure the regulated DBPs in line. So there's some other things you can do too, as well as pH and some other things. So some of the sophisticated drinking water treatment plants in the country are doing these kinds of things. It's a great question.
Okay, well, thank you, Susan. We appreciate that talk.